This is Dr. Heike Bielek from Into Infinity, and today we're going to explore infinity. When we look out at the sky at night, you'll probably be wondering, oh my god, how far does it go? It goes on and on and on and on. It's infinite. But is that the only type of infinity? Let's explore some of the concepts within fractal geometry. Okay, I'm going to throw a stone in water, and that's like a dot. And that dot expands into a circle, the expansion going bigger into infinity out. But what happens with other shapes? Let's look at the triangle and the square. Here we have a square, and let's say we're going to divide each edge of the square into half. And that creates a midpoint on each edge. And what happens? We can create another square, this time at 45 degrees. Now we could do the same thing. We just divide the edge in half and we can create another square. This time the square is actually the same orientation as the first one, just smaller. And then I could do it again. Well, you could guess what happens. I have another rotated square, and then again I have another parallel square. There's an infinity going inwards. The triangle, same game. We just use the halfway point, so division into two, and there we go. We can create another triangle inside. That's, by the way, a very familiar pattern. Links to the so-called chaos game and the Sierpinski triangle. And then we have another division, and then we have the same triangle, just a bit smaller. So you see it's a pattern, and it really goes also into infinity inwards. And we call this infinity in because it goes towards a point, but it never reaches it. What happens though if we're going to use a different kind of ratio? Let's say this is a square, and instead of dividing it into half, let's divide it into 3. And as we divide it into 3, we can create a square made out of 9 squares. Now that we have that, gives you the right kind of ratio where you can do that. Divide it into 3 again, and then you can create another square outside. And then you could do this again. It creates this fractal going outwards, but at the same time, it never exceeds this boundary of a rotated square. And we call this infinity within a boundary. Let's see how it works for the triangle. And when we do that, we create kind of this hexagonal shape in the middle with these triangles, and obviously we could again put a triangle out here and put a triangle out here and a triangle out here. And then we could do it again, and that could continue. Well, this is known as the Koch curve. We see a very familiar pattern because it doesn't exceed another boundary, which in this case, well, that's a hexagon. So looking at infinity within a triangle and square, using different kind of ratios showed us something about what types of infinity exist. When we're dividing the edges into half, it will create this fractal going infinitely in towards the central point. And the same goes with the triangle. And we see after 3 steps, the pattern repeats, and it's kind of like an algorithm, yeah? And the infinity goes infinitely smaller and smaller. So when we divide the edge into 3, it creates this grid whereby we can flip out another square on the outside. And it creates this kind of fractal growing outwards, but it doesn't exceed a boundary. In the case of the square, it's a rotated square. In the case of a triangle, you divide the triangle into 3, you can flip out the triangle, and you can create more and more triangles. The infinity will go outwards, but it will never exceed the boundary of a hexagon. And this principle of fractal geometry, division into 2 going infinitely in and division into 3 going infinitely out, is in fact reflected in our very unique principle called inverse geometry, coming up next.